Chapter 11. In this chapter, which is called synthesis, we will go back to organic chemistry 1 and focus on those reactions that we studied towards the end. Right? So we'll really go over chapter 7 with substitution elimination, chapter 8, addition to alkenes, chapter 9, addition to alkynes, and chapter 10 about radical reactions. Okay, so if you're coming from another school, or you haven't taken organic chemistry 1 after many semesters, so my recommendation is to go back and then brush up on those chapters. Really, that's the only way. There's many reactions I share with you guys on our platform, this sheet, right? That's the one that you guys should have it posted. Alkene reactions, we have many reactions in here about, here they're all numbered, but here you have about 10 reactions. And for alkynes, you have about the same number. Right? For alkynes, you have up to 12 reactions. Okay, and that's only chapter 9 and 8. So you guys have more reaction for chapter 7 and also more reaction for chapter 10. So yeah, we need to remember and be very familiar with these reactions. Okay, remember that in this chapter, I'm never going to ask you for mechanisms. So mechanisms or arrow pushing formalisms is not going to be requested, but because that was the subject or the goal for organic chemistry 1, but we need to know how to use this reaction. So that's why I posted this on our platform, so you guys can tell, right? I mean, every day by day, in the morning, in the afternoon, you can definitely get familiar to these reactions. Okay, so the most important thing for these addition reactions, chapter 8, chapter 9, is the idea of Markovnikov or anti-Markovnikov addition. Okay, so once again, if you don't remember what Markovnikov means, please just go back to chapter 8 and 9. So now on our platform, I also posted the videos that I have for organic chemistry 1, so you guys can also go back to those chapters. Or if you have not taken this organic chemistry 1 class in the previous semester, maybe like 1 year or more, then you can definitely work on those chapters and those concepts. We will need them absolutely. Okay, and then why? The question is like, Professor, I already passed organic chemistry 1. Why are we going to study the synthesis chapter? Well, the idea is that from now on, we will do synthesis on every single functional groups that we're going to be studying. So for example, next chapter is about alcohols. We will do synthesis with alcohols. Then the following will be conjugated dienes. We will do synthesis with dienes. When we do ketones and aldehydes, we will do synthesis with ketones and aldehydes. So we will be doing a lot of synthesis. So this chapter 11 is going to be really like a starting point for us to be in the mood or be really in the strategy. It's really like a game, to be honest, the game of synthesizing molecules. Okay, so let's go back to the share screen. Let's share, go back here. Right. All right. So here we have on these slides, we have here once again the condensed view of this of the share, right, of the reactions. They're even with names. Once again, we don't need to know the mechanisms for these. Okay, so this is another synthesized version. Don't listen to the chapter. Sometimes, depending on the edition of the book, this chapter changes. So this one is supposed to be chapter 9 for our current edition, and the previous one was supposed to be chapter 8. But once again, you know what we are talking about. So don't get really distracted by the chapter number. It's really by the content. Okay, it would be ideal to have this slide with which ones are Markovnikov or anti-Markovnikov, but on the other hand, it's also better because that forces you guys to go back to those chapters and then also try to find out which ones are Markovnikov, which ones are Markovnikov, right? So here, this one is a slide for chapter 10. In chapter 10, we were using radical reactions. Basically, we were doing chlorination and halogenation. So in chlorination and halogenation, we were trying to add chlorine and bromine, right, to alkanes. So basically, we had an alkane, which is a molecule that has no functional groups. Really is a dead molecule, right, because it has nothing to react. But halogenation chlorination and bromination can bring it to another level, right? So now that you have bromine inside, you can do things with this, right? So you can do elimination, or maybe you can do substitution with this bromine. Now, what's the difference between chlorination and bromination? Bromination is more selective, right? So if you have a tertiary carbon and a primary carbon, bromine will selectively add or react with the tertiary, with the higher substitution. The higher the substitution, that's where the bromine is going to target. So for example, chlorination is not as selective. Chlorination, it can either target the tertiary carbon or the primary carbon. So that's why you have a more scattered distribution, 72% and 28%. Bromine, no. So my recommendation, guys, if you want to so you want to halogenate an alkane, definitely go with bromine. Bromine and light. Don't forget the light because it's a radical reaction. We need light to start the reaction. The other one is the HBr, anti-Markovnikov addition. This one uses peroxides. These reactions, all these reactions, they have a mechanism, which we studied in Organic Chemistry 1. We are not going to do the mechanisms now, but remember the reaction. You have an alkene, least attituted this side, most attituted. The HBr and peroxide will add the bromine to the least substituted side. Okay, so if you are producing a chiral center, you will produce the two enantiomers as a result. Okay, so there's another reaction here. If you have an alkene, there is something called allylic bromination, Br2 in light. It will give you the allylic bromination. If you are only having the alkene with plain bromine, you will do the dihalogenation, which is, this is chapter 8. Right? But if you do it with light, it will go towards the allylic side. Okay, so that's the big difference between the two reactions. Normally we do this reaction. If you want to dihalogenate, go to this reaction, you will do it in darkness because you don't want any of the allylic bromination. You do it in darkness, so you will populate most this product. But if you use a potent light, right, a very strong light, right, like it has to be H nu means like light. That's just visible light. So you can put it under the lamp, light bulb, a conventional light bulb, and it will work. So that will speed up this reaction with the allylic bromination. Okay, so you want allylic bromination, bromine in light, and then you will get the bromine in the allylic side. Okay, this one can also be, that's another reactant that is conventionally used, is NBS, is N-bromosuccinimide, right? So N-bromosuccinimide works the same as bromine and light, but this has like a more controlled bromination stage, because this one can give you polybromination. With NBS, we control that polybromination, so you only get one bromination. So for example, what happens if I use bromine in light here, right? You use bromine in light, it will give you bromine here on the tertiary, but since you also have some secondary, right, secondary carbons, it will also add the bromine to the secondary sites. So you don't want that. So NBS is a more controlled bromination, so it will selectively take you to the tertiary only. Okay, so once you guys have the bromine inside, then you can do substitution and elimination, which are the subject for chapter 7, right? So substitutions, chapter 7, and elimination, also the second part of chapter 7. All right, so here, other strategies that we use in Organic Chemistry 1 was chain elongation. Okay, in the case of chain elongation, we had to use acetanilide ion, which is, alkanide, my bad, alkanide ion. The alkanide ion is an excellent nucleophile, and it can combine or do a substitution to an alkyl halide. So here is an alkyl halide. It will do like an SN2 reaction type, SN2 type reaction, and it will add to the alkyne. Okay? And then you can continue doing whatever you need to do with the new alkyne that you're producing. Okay, so let's do it by hand, so you guys know that I'm always hands-on approach. Okay, so things that we will use a lot in this chapter is chain elongation. Chain elongation. What is chain elongation means? Meaning that I need to I need to grow my chain, right? The chain of carbon. So for that, you guys will need an alkyne. Okay, the alkyne. Remember that the alkyne has a hydrogen here. This hydrogen is kind of acidic, so we need a strong base. amide. Normally the amide ion is used for that. You will produce the alkanide ion. This alkanide ion is a very strong nucleophile. As a strong nucleophile, it can do SN2 reactions. So if I have this alkyne, I can make it react with alkyl halide. And it will do an SN2 attack, right? So it will attack here, attack here. What happens? Well, the alkyne will be there, and then it will attack here. That's 1, 2, and 3. 1, 2, and 3. Okay, so it got elongated. So I had 1, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so carbons that I have for this compound. Okay, that is my chain elongation. Now, can I do reaction with this new alkyne that I just produced? Yes, absolutely. You can make some reactions, but I elongated the chain, right? So I went from a 4-carbon chain to a 7-carbon chain. Same thing here, from a 3-carbon chain to a 7-carbon chain. Now, sometimes you guys can play with that role. What do you mean by playing that role? Meaning that if you have a compound, right? So for example, I have this, and they ask me, okay, I need you to make it grow all the way to this one, right? So this one is 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So 7 carbons here, and it's 3 carbons here. Now, you can ask me like, okay, professor, but you gave me the alkyl halide. Okay, so what should I do? Should I make the alkyne from this? No. If you have the alkyl halide, there is no need for you to make the alkyne from this. You can easily say, okay, so I have the halide, and then I will add how many? 1, 2, 3. This one is 7, right? So my alkyne will be 4 carbons long. 1, 2, 3, 4. Yeah. Okay. 1, 2, 3, 4, 5, 6, 7. Yeah, exactly. So the reagent that I'm bringing is already an alkyne. It depends on the scenario, right? The scenario will tell you like, remember to do chain elongation, you need an alkyne and an alkyl halide. Okay. Do I always have to start with the alkyne? No, you can start with the halide and then add the alkyne to it. Okay. So it doesn't necessarily have to be like, 1 plus 2 gives you 3. No, 2 plus 1 also gives you 3. So you guys have to play with that. You have to see like, what is easier for me? Is it easier for me to keep the alkyl halide and add the alkyne, or what is better for me? That's why I say that this one is like a game, like a strategy game that you guys have to make a decision. You want to save steps. You don't want to end up having a synthesis that is like 10 steps long. You want my synthesis, you have 3 steps long or only 4 steps long. So you guys have to decide. All right, so I know to make my chain longer, I need to use an alkyne and an alkyl halide. I'm given the alkyl halide already. Okay, so let's bring in only the alkyne. Okay, so it depends on the scenario. So in this case, for example, if they tell me, okay, what is this? Yeah, same thing here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 6 carbons. Okay, 6 carbon, 4 versus 6 carbons. Of course, this one is a chain elongation. Now, my question is like, what do you guys think would be easier? Remember that you need an alkyl halide and you need an alkyne. What's easier to make from this? The halide. Yes, correct. The halide is easier to make. But why is it easier to make the halide? Because I can make the halide in only one step. What about the alkyne? Can I make the alkyne from a double bond? Yes, you can make the alkyne also from a double bond, but it takes you more steps. Okay, so now you can ask, oh, Professor Navarro, does that mean that we will get penalized if we use more steps? No, 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 I won't penalize versus more steps or less steps, but it will make your work longer. You will have to think more. You have to spend more time. You don't want that. Nobody wants that. So in the halide, I will just need to do a halide. So what could I do? Okay, so if I have that, I will make it with the HBr peroxides. This is an anti-Markovnikov, right? Anti-Markovnikov addition. I'm adding bromide to the least attitude carbon. And to this, I will add the alkyne. 1, 2, 3, 4, 5, 6. Okay. After that, I will get this compound. And that's it. Okay. So you're allowed to do whatever you guys want. Okay. Of course, if the starting material is an alkyne, of course you have to use the alkyne. You're not going to convert the alkyne into an alkyl halide. No, no, that doesn't make any sense. Okay. But now, what to do if you have to actually make the alkyne, right? Well, let's go back to, how to make an alkene, just to brush up a little bit of how to make an alkene. Alkenes are made always from halides. Okay, so I can make an alkene, has to be from a halide. So I can do it in two different ways, Zaitsev or Hoffman. So if you do Zaitsev, you have to use a small base. Oh, space, a strong, small base. So it can be ethoxide, can be methoxide, can be hydroxide, right? Anything. It will give you the most attituted alkene. If you use the other base, which is called terburoxide, right? Terburoxide, it will give you the least attituted alkene, right? Because remember, the alkene can be made this side or this side, right? That one will be my Zaitsev alkene, and this one will be my Hoffman alkene. And so you decide. Now, sometimes in the exams, I mean, in previous semesters, I noticed that I write here a potassium terbutoxide, and then because you guys see the potassium, you want to put the potassium somewhere. I have even seen in exams you guys writing like that. The potassium ion is always an spectator ion. So if you see in the reagent, right, on the reagent arrow, so you see a sodium ethoxide or a sodium hydroxide, right? Does that mean that I need to use sodiums anywhere? No. These ones are called spectator ions. Spectator ions are never used, they're never part of the skeleton of the molecule. Spectator ions, they are only, as the name says, spectators. I mean, they're really not participating in the reaction. The only job of these ions is just to be the counter ion of these bases. Okay, so don't try to put the potassium, don't try to put the sodium, on the chain. Some people even say like minus plus here. That doesn't make any sense. Okay, so sodium and potassium, they are only spectator ions. Same thing, later on we will learn something called a Grignard reagent. Grignard reagent uses magnesium. Magnesium is also an spectator ion. Magnesium has no role in the skeleton of organic compounds. All right, so being clear with that, please don't take it, don't assume, like, for example, if I have this, like for example, this, what if I put potassium cyanide? This is a substitution reaction. Which one is my nucleophile? Cyanide. Okay, but I don't know, for some reason on the quizzes or the exams, I always see like this, potassium. What is potassium doing here? There's no way potassium can be inside of a carbon chain. Okay, so here clearly is potassium and cyanide. So my my nucleophile is cyanide. So the one that should really be here is cyanide. Then you say like, oh, what should I do with potassium? Should I just ignore it? Yes, ignore it, because as I said, it's an spectator ion. So technically you will get KCl, because the Cl leaves and the potassium will also, right, will go with now with this new co-ion, right, the counter ion. So do I need to write this secondary, or let's say like byproducts? No, you don't need to, right? So this one will be the, well, let's say to be more right, more specific, it will be, because this one is an SN2 reaction. SN2 reaction inverts, right, inverts the stereochemistry. Okay, so this is how to make alkenes. This one was an SN2 reaction. Now let's say how to make alkynes. How do we make alkynes? Alkynes can be made from alkenes. Okay, how do I do that? Okay, so to make an alkyne, you guys have to do a dihalogenation, bromine, no peroxide, no light, bromine, and then you guys will get two bromines. trans, okay? Bromine trans. And you want to emphasize the trans, you can do a dash and a wedge, right? Something like this. You can, some people they use like a hollow, right? Hollow wedge. But in my case, I normally use dashes, wedges and dashes. Okay, that emphasizes that it's trans. But just by looking at the molecule up and down, just already gives you the trans. And then you guys are gonna add excess sodium amide. What is this doing? Well, this one is going to eliminate this hydrogen with this bromine, and then this hydrogen with this bromine. That's why you use double. So we call it excess, but it's really two of them. So you guys will get this one. Okay. Now, but since you guys have excess of sodium amide, that hydrogen will also be deprotonated with the excess sodium amide. So you will end up having the alkanide. But you don't want the alkanide, you want the alkyne. So you guys have to close the cycle with either water or H3O plus. Okay. Do I always have to do this? Yes, you have to do that if you are making a terminal alkyne. I must close the cycle with water or acid. Why is that? Because a terminal alkyne is acidic. If a terminal alkyne is acidic, it will get deprotonated in the presence of that strong base. So I need to reprotonate it. How do I reprotonate it? With either water or acid. Okay, H3O plus should be okay. Don't use HCl, don't use, if you want, you can write, diluted acid, right? Diluted, you can use this, diluted acid, diluted acid, or okay, so H plus, you can write that, but don't write HCl, HBr, HNO3, no nitric acid, no, you don't need to specify because it really acidic conditions what we need. Okay, that's how to make alkynes. Any other way how to make alkynes? Well, there are many ways how to make alkynes, but if you have already yeah, you have already a dibromide. Yeah, I already have a dibromide. This is the difference between this dibromide. This dibromide is called geminal dibromide, as opposed to this one. These ones are called vicinal dibromides. Okay, vicinal dibromide, neighboring dibromides. These ones are geminal, meaning that the two bromides are on the same, right, or on the same carbon, but the neighbor has two hydrogens. So this one will go with this one, and this one will go with this one. So what should we do? Excess amide, sodium amide. Sometimes I will write it as sodium amide, or sometimes I will just write plain NH2 minus. Either way works. Remember, sodium is just an spectator. It doesn't really participate in the reaction. So it will eliminate, you will get the step one, but in step two, since this alkyne is going to be terminal, I need to add H3O plus, right? Remember what, like I said before. So you guys will get the same alkyne. Good. Okay. Another example, cyclohexane, two bromines, yeah, two bromines. I need to make an alkyne. How do I do it? Well, in this case, you just add excess amide. Do I need to add acid or water? No, in this case, no. You don't have to. Why? Because the alkyne that you are making is not terminal. It's internal. If the alkyne is internal, then there is no need for you to add water or acid. So the two hydrogens will be eliminated, one with each, and then you guys will get the alkyne. Okay, that's how to make alkynes. All right, so we did first chain elongation. Now there is also chain reduction. Reduction, not oxidation reduction. It's chain reduction in the sense like the length. So there are two ways how that can be done. So one is with the ozonolysis. Both of them are ozonolysis. In this case, my chain goes from 1, 2, 3, 4, 5. If I do ozonolysis in DMS, DMS is dimethyl sulfide, right? It will cleave the molecule right in the middle between the two, right? Between the two carbons of the alkene. So you have 1, 2, 3, 1, 2, 3, and then that 3, if it has a hydrogen, it will be an aldehyde. And the other half, also, if it has a hydrogen, will be another aldehyde. So you see my two compounds, 1, 2, 3, are shorter, right? 1, 2, 3, 4, 5. I go to a 3 and a 2. Oh, but Professor, I only meant to make this three-member, right? Three-carbon chain. That's okay. You can use it and then say, like, out of these two products, I want this. And you can just continue with your synthesis from here. Okay. Another one. Yeah, this one. All three in DMS. It will cleave here, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And on number 5, I have a double O. In this case, it's not an aldehyde, right? Not an aldehyde in the previous case. Why? Because this carbon has no hydrogen. If it has no hydrogen, so you will make a ketone. What happened with this guy? That guy will be this side product. But I don't need this one. That side product, I don't need it. I really needed this guy. Okay, so that's one way how to do like a chain reduction. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, right? So I went from 7 carbons to 6 carbon. Okay, chain. So that's one way how to do a chain reduction. Another chain reduction, very efficient, is to do the decarboxylation with of alkynes, also osmolysis. Okay, so you guys have this compound and you do O3 in water, it will cleave at the alkyne. So it will be 1, 2, 3, 4, and carbon number 4 will be a carboxylic acid. 1, 2, 3, 4. And what happened with this carbon? This carbon will be released as CO2. So you lose it. Okay, but it has to be a terminal alkyne to do that. If you have an internal alkyne, and you do the same ozonolysis, then it will cleave here, but now you will get two carboxylic acids. In this case, since my alkyne is symmetrical, you will get two identical carboxylic acids. 1, 2, 3. Propionic acid, twice, right? 1, 2, 3 carboxylic, 1, 2, 3 carboxylic. So 2. Well, no, it's just this single product. And then that's all, that's what we get. Do we get also carbon dioxide? No, there's no carbon dioxide. You only get carbon dioxide if you have a terminal alkyne. All right. Okay, great. So now let's do some practice problems that we had. I prepared few. Let's see how we do it. Really, there is nothing to teach here other than the strategy. So let's go back to the share screen. Okay, they're asking us here, you have an alcohol, how do I go from an alcohol to the alkyne, right? So there are different ways how to do it, right? So there's the forward reaction, but you can also do the backwards reaction. That's really what they are trying to tell you here. With this green, right? Green shade, green color is telling you like focus on the backward, right? The one step behind. So how do I make an alkyne? Well, you make an alkyne from halides, right? Dihalides. That's how you make an alkyne. That's exactly what we just went over. So it can be either the two bromines here, or the bromines vicinal, or the geminal bromines terminal, right? And then, of course, these dibromides have to come from an alkene, right? And this alkene will come from the alcohol. So that's exactly what this is telling you. It's like you're gonna have to do from this side, this one, the vicinal dibromide will be eliminated with second step with water to produce the alkyne. But now, how is this one? How was this created? The vicinal dihalide, dibromide, it came from an alkene. An alkene used to be here. You brominated it. And now how do I make that alkene? Is by the elimination. I need to do an elimination with OTS. What is this type of elimination? Well, that elimination can be a terburoxide because it's a terminal alkene that I'm producing. So I use terburoxide, potassium terburoxide, and I produce elimination. Now, why do I have to use OTS, right? Why is the purpose of OTS? Well, OTS is because of the OH is a bad leaving group. Since OH is a bad leaving group, then I need to activate it. So that activation is tosylation, and that's what you guys will do, tosylation in pyridine. Pyridine is just a solvent. So you are tosylating the OH, making it a good leaving group. Now you make a terminal alkene by losing the terburoxide, and then the alkene that you produce undergoes dihalogenation, trans, vicinal, and then this vicinal dihalide, dibromide, it will undergo the exhaustive elimination to produce the alkyne. Okay. Okay, so actually let's start by doing those two. Let me write it. I have more examples, definitely. So this chapter is all about practice. So if we don't practice, that's really not. By the way, here this slide says homework, but yeah, you don't need to do it as homework. Yeah, let's do only the first one. I'm sure that you guys also want to see the second one, but let's see. All right. Okay. Okay. So that one was the first problem. Clearly, we are in front of a chain elongation, correct? Right? So we all agree that chain elongation, 1, 2, 3, 4, 4 carbons, 1, 2, 3, 4, 5, 6, 6 carbons. Okay, great. So 6 carbons versus, so that means that I'm doing an alkanite, right? Now, it's the same question I'm asking you now. What is it easier? I know that for chain elongation, I need an alkyl halide, and I also need an alkyne. So what is easier for me? To make the alkyne or to make the alkyl halide from here? Of course, it's easier for me to do the alkyl halide. Now, Professor, why are you doing the forward? Why are you not doing the backwards reaction? I could do it. I could do it either way. Okay, so let's do the backwards. I mean, I was starting with the forward, but we can definitely go the backwards. Now, aldehydes. How do we make aldehydes? Okay, so let's go to this sheet. No aldehyde, no aldehyde, no aldehyde, no aldehyde, 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 aldehyde here. How do I get aldehydes? From ozonolysis. Okay, ozonolysis of alkenes. Okay, but what is the disadvantage of that? That reaction, I cleave. I have to cut something. Do I need to cut something to get an aldehyde? No. Actually, I want to elongate it. I want to make it longer. So I can't really use this reaction. This reaction doesn't help me. This reaction shortens my chain. I need to do something that makes it longer. What makes it longer, or at least the same length? This reaction. 1, 2, 3, 1, 2, 3. So I'm making an aldehyde with the same length as my alkyne. Any other aldehyde? No, aldehyde, aldehyde, aldehyde? No, no aldehyde. So that means that this one should be my reaction. So this guy is really coming from a step backwards from an alkyne. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yes. Okay. Alkyne. That was before that with the same length. I cannot use the other reaction because with the other reaction, we will make it shorter. I don't want to make it shorter. I actually want to make it longer or same length or longer. So in this case, I use that. The reagent was this, right? Hydroboration. Professor, do we need to know these reagents? Yes, we need to know these reagents. Okay, now how do I make an alkyne from from this particular compound? Okay, so it has to be longer. Then I can just add it, right? As we said before, this one can be the halide. Okay, so let's make it into a halide. I need a terminal. So HBr peroxide. It will make it longer. 1, 2, 3, 4, 1, 2, 3, 4, good. And then how do I go from here to here? I'll just do, I need two more carbons, right? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So I will use this halide and this alkyne. I'm just using these arrows to just to show what happens. I mean, you don't have to. Okay? It adds, and then you guys get this compound. Ta-da! And then you finish your synthesis. Professor, can I make the alkyne from this and then add the halide? Yes, but it will take you more steps. Right? It will be longer, make a longer synthesis. Here now, next, same, six, it's like 6 carbons, 7, 8, 6, 7, 8, 9, elongation. Definitely is an elongation. Okay, now, but this elongation is a little bit tricky, right? Why is it tricky? Because I need to make this one the alkyne. How do you know, Professor, this one has to be the alkyne? Because remember that when you add a triple bond, when you add the alkyne, automatically you are adding what? You are adding 2 carbons. If I add 2 carbons here, I will pass the length, right? Because it's 1, 2, 1, 2, 3. If I add the alkyne here, I will pass the length. 1, 2, sorry, 1, 2, sorry, 1, 2, 3, 4. So I don't want that, right? If I add the alkyne. So I need to have the same length. So this one is a kind of like a tricky question because this question is actually asking me make the alkyne from this compound. Once again, how do I know that? Because if I add the alkyne, I'm adding at least 2 carbons. You cannot add an alkyne that has only 1 carbon. Alkynes always need at least 2 carbons. So in these 2 carbons, if I add 2 carbons here, I will pass the length that I want, right? Which I definitely don't want. So I need to make it the alkyne from here. Now, this product is a transalkene. How do I make transalkenes? Transalkenes can be made from alkynes. Alkyne in sodium in liquid ammonia give me trans. So that means that this guy used to be an alkyne. Like this. Okay. 1, 2, 3, 1, 2, 3, alkyne. What did I do to this? Sodium in liquid ammonia to make it trans. Do I have to do that trans? Can I use Lingler catalyst with hydrogen? No, because that one will give you the cis. And you cannot just use plain hydrogen in palladium because hydrogen palladium will reduce it to fully to alkane. Okay, now here to here, how do I make an alkyne? Okay, so I have to make the alkyne here. And of course, the alkyne has to be terminal. So how do I make an alkyne? From an alkyl halide. This one is not an alkyl halide, so then let's make the alkyl halide. HBr peroxide. You will say, Professor, why HBr peroxide? Because I want the HBr on the least substituted. Why here? Because I want the alkyne here. Remember, I want to elongate from this side. I don't want to elongate this side. I want to elongate from this side. So if I want to elongate this way, then I have to do the bromination on this carbon. If I want to elongate this way, then I will want the Br here, but I don't want the Br there. I want Br terminal. So I will put the Br on the least attitude. Okay, good. Now I need to make the alkene. How do I make the alkene? Terburoxide. Alkene. And now I go to the alkyne. Br2. This is trans. Excess amide. Okay, excess amide. Now, do I need to get the water? Professor, you said water before. Yes, I said water before if you want to make the neutral alkyne. But in this case, actually, I want to make the alkanite. So why? Because if I add methyl chloride, it will alkylate it. This methyl will be this methyl right here. And then I completed my path. This long, very long. Professor, are the exam or quizzes questions gonna be this long? No, no, no. Maybe you guys will find synthesis like this. This is 3 steps, maximum 4 steps. But this one I think is too much. 1, 2, 3, 4, 5, 6. Yeah, no, that's too long. Okay, you will not encounter a problem like that. Clear? Everything clear? Please remember that I always have, sessions for questions. If you guys have in my office hours, you can always visit me in my office or during the labs. I'm always available. All right. So here I have some other reactions, okay, that you might want to try. We will do it as a class. Please pause the video, right? If you think that, it is you want to try by yourself, that one will be a good time to pause it. Okay, so in this particular problem, they want I'm gonna change. I want some color in my life. They want me to go from a transalkene to a cis-alkene. How do I do that? There is one reaction which is through alkynes. This is, sorry, what is it? Yeah, the cis-alkene is using an alkyne using the Linglar's catalyst. Okay, so that means that the backward, right, step behind was an alkyne. So somebody use here H2 in Linglar's catalyst. Okay. Now, how can I make an alkyne from an alkene? We just did it. And to be honest, it's going to be very difficult to remember at the beginning because it's the first time you do it. But if you guys practice, you will do, okay, alkyne, PR, elimination, amide, water. You will do it so many times that you will get used to it. Just as soon as somebody asks you like, oh, make an alkyne, you know automatically that you guys have to do this. Bromine, it will give you the dibromide, right? And then I use excess amide. Excess amide. And that's it. Do I need to use water here? No. Why? Because it's an internal alkyne. So see, this synthesis is done. So double bond, I open the double bond, right? Double bond, you have now a trans dibromide, and then add excess amide. So you guys will have that, double elimination, and it will give you the catalyst. Good. Great. You see, 3 steps, the synthesis. Sometimes it will be 4, but not really. Okay, another one. So what is this? Always count. I forgot to count here, but Kiko's count is obvious. 1, 2, 3, 4, 1, 2, 3, 4. So there was no elongation, no shortening of the chain. So I didn't really have to deal with that. 1, 2, 3, 4, 4 carbons. 1, 2, 3. Okay, so here I'm shortening the chain. What this helps me to shorten the chain? Well, first I have on alkynes. I can shorten it with the ozonolysis, right? But I also know that I can shorten that with ozonolysis on alkenes. I cleave the double bond. Okay, so most likely I will have to do that. I have to cut it. Why? Because the alkyne gives me carboxylic acids, and this is not a carboxylic acid. This is an aldehyde. So I will definitely have to do the alkene. Now, where do I want the alkene? Well, I don't want the alkene internal, because if I do it internal, right, it will cut it in twos, right? 1, 2, 3, 4. It will cut it right in the middle. I want it terminal. So how can I do the elimination terminal? With terburoxide. It's a Hoffman elimination base, right? You have this alkene. And now to this, I will do the ozonolysis. O3 in DMS. It will cleave here, and you will get here actually 2 products. Those 2 will be the product. And that's the product that you want. This one is a side product, which you just eliminate. Okay? See, this synthesis has only 2 steps. That's all. Great, next one. Okay, so I have an internal OH and they want me to move it to a terminal OH. Okay, elongation, shortening, let's see, 1, 2, 3, 4. 1, 2, 3, 4. So same number of carbons. So I'm not adding, I'm not cutting. So all I need to do is a terminal OH. How do I make terminal OHs? With hydroboration. Hydroboration is the one that allows you to put an OH on the terminal. Now, Professor, how do you know that? I mean, definitely you can, this synthesis to you seems so easy because you know those reactions. So what's the only way how I can learn it? Same way. So you have to learn the reactions. You know that how do I put an OH terminal? With hydroboration. That's why it was so important, chapter 8, chapter 9. Is there any shortcut, something? Can I use flashcards? No. We cannot have flashcards, anything during the exam, during the quizzes. During homework, open book, something, you can just use whatever you want. But during the exams and quizzes, we are not allowed to have this sheet or any type. Okay, so we have to remember them, unfortunately. That's the only way how we are going to learn these reactions. Otherwise, it would be too easy, right? If they give you the tools just to put it together, it's really not the idea. So we have to know those reactions. Okay, OHs, I can make OHs Markovnikov or anti-Markovnikov. In this case, it's terminal OH. Therefore, it's an anti-Markovnikov. The OH used to be there. So this carbon is this carbon. Okay. Now, how do I make this alkene from this OH? Well, first I know that OHs are bad leaving groups. So to make it a good leaving group, I will use a reagent which is called tosyl chloride in pyridine. That tosyl chloride in pyridine will make my OH into an OTS, tosylate, which is a good leaving group. Now, that good leaving group can be eliminated now. But now this good leaving group can be eliminated CHE240 or it can be eliminated Hoffman. In this case, I wanted Hoffman. Right? Hoffman is the least substituted. So I'm going to use a particular base which is called terburoxide. Okay. Once again, sometimes I write potassium terburoxide or I just write plain terburoxide. So how many steps? 1, 2, 3 steps for this synthesis. This one. All right, so this one is a little bit more complicated. I have a diol. Apparently the diol looks cis, right? You looked at the wedge means it's a cis diol. What reaction allows me to make a cis diol? Cis diols here. OH, OH, wedge. This one is a trans diol, wedge dash. Okay. What about from alkynes? Can I make diols from alkynes? Let's see. Diols, no diols. So my only chance is with alkene. So I need an alkene, and I will use either potassium permanganate in sodium hydroxide or osmium tetroxide with sodium bisulfite. Okay, so that means that this guy came from an alkene with osmium tetroxide, sodium bisulfite. Okay. Now, Professor, how do I make this alkene from this OH? Okay, that one, you can say, can I use the same thing that you did here? Yeah, you can do that. But there is another shortcut I will show you, right? I mean, let's say tosyl chloride in pyridine. Yes, you guys will get the OTS. And then after this OTS, you can do elimination. But of course, in this case, you will do a CHE elimination. So you can use ethoxide. Okay. But the shortcut, what is that shortcut that you mentioned, Professor? That shortcut that I mentioned is that the alcohols have a specific property. The alcohols can be eliminated if you use concentrated sulfuric acid. Only if you want to produce the CHE. So why didn't you use it here, Professor? Oh, I didn't use it here because I needed to make the Hoffman alkene. I didn't want to do the CHE alkene. If I wanted to do the internal alkene, then I would just cut it all these 2 steps just with sulfuric acid. But I want the Hoffman. So if I want the Hoffman, I have to do those 2. Okay, but if I want decisive, I can do a shortcut and then do sulfuric acid, takes me to the alkene, and then on the alkene, I do the dihydroxylation. All right, good, clear. Okay, next we have 4 more problems to do. This one is a chain elongation, yeah, clear. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay, so I'm adding 3 carbon chain. So once again, you guys decide. Chain elongation has to go through an alkanite, right? Alkanite ion. So, okay, so to me, the easier, now that we have done many of these problems, I mean, chain elongation, my recommendation is convert this into the alkyl halide, HBr peroxide. 1, 2, 3, 4, 1, 2, 3, 4. And to this, I add what? I add the 3 carbons, and the 3 carbon will have, all right. So to continue with the elongation, now we have to add the remaining, right? So it's 3 more carbons. So I will have the alkyne, right? It's 3 carbons here, 1, 2, 3, alkyne, and then it will get elongated. Dun, dun. 1, 2, 3, 4, 1, 2, 3, 4. Okay. Okay. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yes. And then to go from this alkyne to the single bond, I just use hydrogen in palladium, and it gets fully reduced. Okay. So for the next one, so we have here dibromide. Okay, so for dibromide, I'm starting with an alkane. So the alkane, I can use bromine in light. Remember, it has to be light. So with the light, I get the bromine, monobromination. And now how do I get the dihalide? Well, the dihalide, the only way how I can get a dihalide is from an alkene, bromine alone. Don't use bromine in light. And now how do I go from here to here? Well, from here to here, I just use ethoxide, right? To do an elimination. Okay, that's when it's a need to reaction. I get the alkene and then I do the bromine. You see the way how I'm doing it, guys? So sometimes I go back, I go forward, then I go backwards, and then I connect the dots. Or here, I was doing fully the forward strategy, or like in previous cases, I do the backwards strategy, right? So it depends on how, the way how you prefer it. I'm just giving you different options, and then based on those options, you guys will determine. All right, so this one, the last two synthesis, right? So we have this alkane. The only way how you can bring to life, alkane is by doing the halogenation, right? Radical halogenation. Bromine in light. So I will get, remember, bromine always goes to the most substituted carbon. My only tertiary carbon will be this one. Now, how do I go from here to here? Well, I'm having an internal bromide, and here I have a terminal bromide. Terminal bromides, the only way how I can make a terminal bromide is from an alkene using HBr peroxides. And now, how do I go from here to here? Well, I'm having here a terminal alkene, and here I'm making the alkene right here. The only way I can do that is with terburoxide, which is the Hoffman base. Okay, Hoffman base. If I use ethoxide, it will give me an alkene here, which I don't want. I don't want an internal. I want a terminal. Okay. And our last mechanism, synthesis, will be this conversion. A ketone. How can I make a ketone? I can make ketone from ozonolysis. But remember, when you make a ketone from ozonolysis, you are cutting, you are cleaving. Okay. The other way is by ketone here, alkynes. Alkynes with oxymercuration, right? I can get a ketone, and then the length doesn't change. 1, 2, 3, 1, 2, 3. So that's the one that I want. Why? Because I'm not changing the number of carbons. So here, it used to be an alkyne, and then I was doing sulfuric acid, mercury sulfate in water. Okay, that's how you go from alkyne to, and I would say that that would be the most difficult part of a synthesis. It's always that first step backwards. Once you guys have that step backwards, then you know how to figure it out, right? So how to go from alkene to alkyne. So alkene to alkyne, I just use bromine. I get dibromite. And from here to here, I just use excess amide, right? All right. Good. So that's the I complete the cycle, right? One backwards, one forward, and then I tie, I connect the dots, right? And then that's how you, in this case, I'm making this different synthesis. Okay. So there are different examples. Remember, guys, that we have multiple all quizzes and all exams which you guys can use for this particular chapter. Please use all the resources. Ask me questions if you want to, you want a particular problem to be explained, and please study all these reactions, this chapter 8 and sorry, chapter 9 and chapter 8 for alkene addition. Okay, so let me know you have questions. Have a wonderful day.